So we're trying to decide whether or not this ball hits the can. We've decided that it's a parabola, right, Steve? What would you call this point somewhere in here? No, come on, fancy math term. Vertex. Has the ball reached its vertex yet? How would you know that it's reached its vertex?
The highest point.
Yeah, but what if you only had up to the highest point? Let's just say the highest point is like right there, but let's say that the picture stopped after that. How would you know that was the highest point?
Because it like curved almost to the
The slope would be 0? Okay, so like here we could use like tangents and we could figure out slope. And I think we can all agree that the slope isn't even close to 0 yet, is it? Right? Okay, so if you had to figure out, does this ball hit the can, how would you do that? Any ideas? There's lots of different ways you could do it, but anyone got any ideas in here? Say again? Okay, so you're suggesting that we should try to find this distance here. How would we do that? What might be a way to do that? You could take out a ruler, that's true, but you would not be measuring actual distance, you would be measuring the distance on the picture, right? You'd be measuring the distance on the picture. Does it matter? Because whether it's in real life or in picture, the ball still has to go in the can. So if you measure that like at, I don't know, 23 centimeters, would that be okay to say the can is 23 centimeters away?
Yeah.
You could. What's one thing that you can guarantee, one number that you can guarantee about this picture? There's only one. No, it doesn't start at 0 velocity. Like what? That's the only thing you can say for sure. G is equal to minus 9.8, right? That's the only thing you can guarantee. If you had to guess in real life how far apart the guy and the garbage can are, what would you guess?
15 yards.
15 yards. Why do you say that?
20.
20
yards.
Yeah, I know it's 20 yards.
Okay, so you think it's 20 yards. Do you think the distance from his foot right here to that line is the same as that distance from there to there?
Yeah.
Just
Yeah?
The picture's taken.
The lines are there.
The way the picture's
Each
taken,
10
it's just
yards.
a little off.
So what you're saying is the person that took the picture didn't stand in the middle?
No.
And that's why that line's like that?
They stood halfway in between the 10-yard line and that guy.
It's on
And that guy.
And they took it at an angle.
Yeah.
Okay. Is there anything in the picture that you could use to determine the scale?
The lines.
You could, if you assume that they're 10 yards apart.
Well, it's a,
It's actually, I did some investigating, and it's not a football field.
Okay, because that building was,
that's,
I think that'd be pretty far apart.
Like right from there to there?
Yeah, if you could.
But remember, that's in the distance, right? The farther back you go, right? What about chain link fences like this? Do you think that distance on chain link fences is uniform throughout North America?
no.
Building standard.
Probably. Anyone want to hazard a guess what it is?
Or
Between each post. A meter?
No.
Probably 8 or 10 feet would be my guess. But again, that's like in the distance, right? So if we measured that to like say 1.5 centimeters and we said that's equal to 10 feet, would 1.5 centimeters here be 10 feet? At the front of the picture? No. So the fence really doesn't help us. What about the height of the guy? Could we use that to figure out? We could estimate. John? We could use the garbage can. Would you agree that most Rubbermaid garbage cans like that are probably a standard height?
Yes.
That, I think, is true. So if we could find a garbage can like that, we could figure out the height and therefore the scale. And once we had the scale, then you should be able to figure out, well, even if you took a ruler and measured this distance, could that give you the peak?
Wouldn't a trash can be just for volume, not for height? You don't have standard volume about standard height.
They make them in the same factory, one after the other. Wouldn't they be the same height? I'm going to hand out some rulers, and I'm going to see if you can tell me if it hits the garbage can or not. No, what if I had a magical website like this, where I've got the picture? It's not cheating.
We don't have computers.
Well, come on up here, right? So here's the guy. Here's the garbage can. Here's the... Come on up, Zach. Zach's going to try to make the parabola fit the trajectory. And I know it's kind of hard to see, I understand, but do your best.
How do I flip it? How do I flip it? How do I flip it?
Negative. It's a negative squared graph.
Yeah, but how does it let me do that?
You adjust these slider doohickers things.
That's
here.
all I can do?
H and the K.
Okay.
How are we going to make it negative?
You gotta flip it. You have to make this a negative on the front.
Okay.
Yeah, but I don't know how to do
Can you
that.
just click in here?
Oh, you can just click in there.
Yeah.
Negative.
That's not touchscreen, man.
It's not a touchscreen. There we go.
Oh.
Now we're going.
Now we're cooking with gas.
Now let's. How do I move it? Oh, I have to move it
Gotta
with
move the
this.
sliders.
There we go.
That's a little bit high, don't you think, Risky?
I don't know. Got to change the scale here somehow, because this is maxed out. Oh no! Like, here we go.
What is the K value do?
Nope. Go up.
A value makes it taller.
Hello? Oh, sure.
How do I make it? How do I make it like this? Is that the H value I need to change?
Well, keep looking. No, it would be.
It'd be the.
Oh, I didn't get that.
Here, line it up with the guy. Where's his hand? Somewhere in there.
It's the number with the minus, isn't it?
You need the middle. You need the middle. You can actually. Like the problem. Yeah.
What do I do here, Steve?
Put in 2 up there. Negative.
Where? In front of the X?
No. Outside the bracket by the name. 2 there. So, oh, just kidding. Put a 0.5. Put a 0.5. Put a 0.5. Okay. Put a 0.2.
Okay. There we go. That's good. Wider yet?
Oh.
Now let me try moving into position here. No, that's not the one. There we go.
Oh, Zach, give me a counter. Oh, no, a little wider. 0.05. No, 0.09. Yeah, 0.09. That's gotta be cool. Oh, that's gotta be exact. Oh, no, that's his hand starting up there. He had it on his hand there. Oh, that's gotta be close. That's gotta be beauty. He doesn't make it. Oh, wait.
That's not it. Can't you see the ball way up here?
Hold it down.
Oh, but
I was looking at his hand here. I was looking at his hand.
That's one possible trajectory that would make. Is there more than one trajectory that would make it fit? Can make it?
Well, we got a trajectory right here, and it's pretty close.
Infinite?
Well, other than like, to a certain degree.
Infinite.
Yes.
The higher you go, the
Harder you have to throw it.
That's true.
So I really want to go up here. There we go.
Oh, you gotta done.
Let's try this again.
You gotta make that like a point. 7.
No, we want less now because I moved it.
Yeah.
Oh. Screwed something up. There we go.
You know what you could do here, Zach, if you want?
Oh, okay.
I think you can do this. Let me just see if you do this.
Let's solve for it.
I think I can put
Slide.
insert.
Why do you think?
That would be nice if I had that on a
Yeah, a
small-
slider, eh?
Yeah.
How do I insert a slider?
So using the vector photo.
Right here, maybe? Add?
Maybe.
Oh, now you got rid of that negative.
Add item.
You probably want to leave the negative in there.
No, I don't know.
Because that's the only way you get it.
Oh, I bet you I put like something like an A. There we go. Add slider. Now we're cooking.
What's an A slider do?
Well, that's going to be the, yeah.
Oh.
Oh. Okay.
Go crazy now.
I was having fun.
on the problem.
Okay, now go over. No, which one is it? Okay, here we go.
Oh, yeah, I equals X plus C.
This is.
I might.
Show them on the flags, on the problem. Would it help you if I told you that I know the guy happens to be 6'6"? Would that help? Can you tell based on his height in the garbage can? Can you say, yeah, he's actually taller than average?
How do you know these things?
I asked him. I found out his name and I asked him. No, it's not. He's another physics teacher, and this is what he does for a living.
Makes it difficult to see pictures.
That looks pretty good.
Yeah.
It doesn't really line up,
It's not
but
where the balls at.
well,
Don't you see the balls on there?
yeah, I can. But how do you?
They're right here, man.
Okay, I'll try to get it to
How
line
high
up
are
with the
we,
wall.
or are we saying that garbage can is? Because he's 3 times taller than that, so he could be like a 9-foot giant.
He's not. He's 6'6".
You called him up or what?
I didn't call him up. I emailed him.
9 feet.
Okay, here we go. It's getting closer.
No, he's a physics teacher that does this in his class. He says, we're not leaving today until you can tell me definitively yes or no.
We got a problem. I can't go lower than this.
Look how tall he is. Looks further than you think. I see like 2. Do you measure from his hand or his head?
From his feet.
Well, you probably got to measure from his hand right there. You gotta sort of estimate.
We need it more accurate than this.
Yeah?
Bennett, because
We need like.
when you go there, you see that's too narrow, and then this is too wide.
What?
You need to put a 100 in there.
Okay, so you can probably type in it now.
Can I just type in?
Yeah.
Okay.
It's not touch screen, Zach.
Wait. Oh, that's way too much. Okay.
09.
I want 9.
08.
8? Okay. 8 it is.
Now you're getting close.
Now it's probably.
075. Just kidding, I don't even know.
It's right here though, isn't it?
Yeah, I can move it a little bit.
It's right here. Now it's up here. Would it be easier to find data points to come up with the equation ourselves?
Probably.
Maybe.
To write ourselves a
Should we stop, Zach? Are we done?
Yeah, I'm struggling here.
Yeah.
Okay, maybe. I want to get it, but I'm kind of struggling.
Oh, you know about it. Oh, Zach.
That's pretty close, right?
Yeah, but now I need to get that.
Touching the garbage can, nor the person's hand.
I need it. It's.
Do you know the answer to this question? Did you make it?
No.
He went out there to get the camera.
It didn't go in the can. I think I actually have video.
Go
So well, there's multiple videos, and one of them does it camp if we don't think it's this one. But we're probably done, Zach. That's good.
Okay.
Yeah.
Okay.
The point of all this is.
That was fun.
Matt needs to wake up. Was that fun?
I thought.
Yeah, I'm glad. The point of all this is, I want you to think about the velocity of the tennis ball as it flies through the air. Does it have components? I look for my tennis ball.
Air resistance.
I'm going to throw it at Steve, okay? Can you catch Steve?
Of course.
Is it a parabola shape, right? Does the velocity of the ball have components?
Going from like vertical and horizontal?
Yeah. Does it? It's an arc? Of course it does, right? So what are those components? Horizontal and vertical. Okay. Quinn, pay attention, quit puzzling. What is affecting the vertical component? How hard I throw it?
Air resistance or some air resistance.
Maybe some air resistance.
The angle?
We're gonna ignore air resistance in our study. So I didn't want to discount it, but yeah, discount too hard there. What'd you say? Oh, so I'll say right here. How hard I throw it?
The angle.
The angle and gravity. The vertical is affected by how hard I throw it, the angle and the gravity. Okay, let's talk horizontal twin. What affects the horizontal speed?
How hard to throw it?
And
Angle.
the angle? Well, the angle of release, right? What would you name it to give that angle have? The angle of release.
Theta.
Oh, what name? Like words.
I don't know.
Okay? I mean, it would be called theta, but in a word problem, what would you anticipate it might be called? It's an angle. Angle of release or launch angle, right? Maybe something like that. What affected the vertical?
Gravity.
Gravity. And gravity is a force, and it's an acceleration which is down. But what about horizontally? Is there a force? Friction with what? Just air resistance, which we've already established is fairly minimal. Now, when Steve and Jason go golfing, and anyone else, I don't know, I know you guys are golfing. When you go golfing, Steve, does your golf shot look like a perfect parabola?
Oh, I bet you. Stevie flop shot.
Yeah?
No, not always.
In fact, not at all, my friend. Usually when you hit a ball, it goes up like this, and then it gets to some magical point, and what does it normally do? It drops straight down. Why does it do that?
Because it loses its velocity.
It does, because there is air resistance in the real world. So it's not a parabola. I think it's called like a lotus or I can't even remember what it's called. I don't know. But it goes up like this, especially like if you hit like an 8-iron there, like on number 16, right? From behind the pond, right? 8-iron from 120 yards out. You probably only hit like a pitching wedge, and I'm kind of weak. So you hit the pitching wedge from 120 out, and it goes up like this, right? And then what happens? You hit that pitching wedge, so it does what? So that it drops straight down and it stops quickly. Why does it stop quick? Why does it stop quickly? Because it's falling
It's more vertical.
straight down. And there's no horizontal. That's why you get that big thing. Okay, so I've done a lot of blathering here, lots of yakking. Let's go to, I think we're more or less done with this whole. Let's go with this. Here's the unit in a nutshell. Here's the unit in a nutshell. It's not very long at all.
How many?
Like 2 weeks.
That's 2 weeks.
Like 2 weeks.
Is this one of the harder units?
I wouldn't say that. There's really not a lot for me to teach you. There are 2 or 3 labs depending on the weather, depending on what we want to do. We will do at least 2 of them, maybe 3. Okay, so you will solve simple free-fall problems using the special equations for constant acceleration, include horizontal and vertical components of motion of the curved path of the projectile without air resistance, Zach. We will draw free body diagrams for a projectile at various points along its path, with and without air resistance. We will calculate the horizontal and vertical components with respect to velocity and position of a projectile at various points along its path. Calculate components, and then the big one, which is really the main one, solve problems for projectiles launched horizontally and at various angles to the horizontal to calculate maximum height, range, and overall time of flight of the projectile.
What would you rank this unit in like hardness compared to the other ones?
Well, I think it's actually easy because there's different types of problems, but it's all really just applying slightly different logic to these different situations. But it's really all boiling down to projectiles, which have many things in common. Let's talk about the 7 types of problems. So there's horizontal ground straight up. You've done that in grade 11 already. Horizontal ground straight up.
I got that.
Zach launches his potato gun straight up,
I got that question.
and then has to get out of the way because it's coming down just as fast as it went up. Right? No? You can't get away?
Doesn't get that close to you.
That's because of the wind, right? So on a windless day. Horizontal ground straight up. What about horizontal ground at an angle? Well, that would be simply, and that should be a parabola. Right? So, kinda like the guy throwing in the garbage can. Kinda. More like Steve hitting an 8-iron out of the golf course, because it's from the ground to the ground, right? What about off a cliff dropped? What would that look like? Well, there's your cliff, and you're just dropping it, right? Did in grade 11, did in grade 11, because it's one-dimensional. Off a cliff thrown, all that means, what's the initial velocity here? Off a cliff thrown, the initial velocity is some value, maybe -5. Did we do questions like that in grade 11? You might have. It's possible. Again, one-dimensional. off a cliff, thrown up and then down. I don't mean you got sick, you barfed. I mean like, you know, the ball is thrown up on the edge and then comes straight back down like that. Again, one-dimensional, may have done in grade 11. No, off a cliff projected horizontally. What would that look like? Yeah. Imagine a guy driving a car off a cliff, maybe Thelma and Louise. You seen that movie?
Oh my god. Such a bad reference. What?
Don't do Thelma and Louise not drive a car off a cliff at the end?
So, really for everybody else.
Oh, yeah, I guess I did. Sorry about
That's
that.
the entire
Yeah, but
movie.
do we
One
really
gonna watch it,
care?
don't worry.
Off a cliff projected at an angle.
Now they're jumping at it.
Okay, so now it's jumping, yeah. Now Thelma and Louise hit a jumping. Yeah. Which one of those would be like the Evel Knievel one?
7.
Oh, yeah. That is the big daddy. If you can do number 7,
Actually, it might be more like number 5.
Every ball I go.
yeah, good point. I'm going to launch straight up and I'm going to go across it.
They still didn't make it.
No, I know. Okay. So yeah, those are the 7 types of problems. Basically what I'm going to do is I do 3 days of sample ones. I give you some time to work. We do some labs that involve them and then we make it for a test. That's what it boils down to. Okay? But we will do actual hands-on where you're going to try to find how fast something's going and where it's going to land. You're going to do this the first lab here. You're going to have to figure out how fast it's being rolled across the table and tell me where it's going to land. We're going to use the table. Okay. Let's do some theory stuff. Oh, I got some videos for you too. Oh, you need clickers for this. We got to hustle.
Can we watch the video?
We'll get to the videos there at the end.
Oh.
Okay. Yeah, go grab yourself a clicker. I'll pause for a second.
Zach. Zach.
Okay, so after this, you're going to be able to draw the horizontal and vertical vectors for a projectile at various points. That's one of the outcomes. And calculate horizontal and vertical components. You already know how to do that. It really isn't that big of a deal. In fact, this whole unit just takes a whole bunch of stuff that you already know and just sort of puts it together. So it's a good kind of review. Earlier we discussed vector quantities, velocity, acceleration. Since only horizontal and vertical motion was considered, we did not need to know about vector addition or the techniques of vector resolution. But for objects projected at angles other than straight up or down, you do. A projectile is any object that is projected by some means and continues in motion by its own inertia. Because an object in motion will stay in motion. A cannonball shot from a cannon, a stone thrown in the air, a ball that rolls off the edge of a table are all projectiles. These projectiles follow curved paths that at first thought seem complicated. However, these paths are surprisingly simple when you look at the horizontal and vertical components of motion separately. Let's do that. The horizontal component of motion for a projectile is no more complex than the horizontal motion of a bowling ball rolling freely along a level bowling alley. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. It covers equal distances in equal intervals of time. The distances between them are the same. It rolls of its own inertia, with no component of force acting in its direction of motion. It rolls without accelerating. The horizontal part of a projectile's motion is just like the bowling ball's motion along the alley, especially this part. True if you disregard air resistance, which we will do. Interestingly enough, and this, my friends, is the paragraph that explains the entire unit. Interestingly enough, the horizontal component of motion for a projectile is completely independent of the vertical component. Each acts independently of the other. Okay? It doesn't matter how fast it's going up. That has no effect on the sideways. Okay? You guys don't have this.
There we go.
I apologize. Oh. I'm still trying to write that first question.
Usually start with that.
Yeah, we get it. That's true.
My mistake. I'm so excited to get into this.
I'm just
You go at home. How's that?
To get in the incident.
Oh, right. Okay, so yeah, highlight that box. Horizontal and vertical, completely independent. There is only gravity for vertical. Quinn, put that away. Listen to me. There is only gravity for vertical. If I see you putting gravity for horizontal, I will shake my fist at you. Gravity does not act horizontally. It only acts down. I'll be like Grandpa Simpson. When I was a kid, we didn't have gravity, and we liked it. The multiple flash exposure of figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. Investigate the photo carefully. There's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components of motion separately. There are two important things to notice. The first is that the ball's horizontal component of motion doesn't change as the falling ball moves sideways. Now, you can't see it, but if I draw lines like this, I'm going to draw them at the front of the ball. Those lines, oh, I didn't draw it very straight. Those lines are the same distance apart. How come?
Because the vertical doesn't.
The horizontal doesn't change. There is no gravity acting horizontally. Okay? So the ball's horizontal component doesn't change. The ball travels the same horizontal distance in equal times between each flash. That's because there's no component of gravitational force acting horizontally. Gravity acts only downward. So the only area of acceleration of the ball is downward. The second thing to note from the photo is that the vertical positions become farther apart with time. The distances traveled vertically are the same as if the ball were simply dropped. I actually have a device that will show this. I'll bring it up next class. Look at that line right there. Oh, that was a mistake. Look at the white line right here. The red ball over here on the left is completely lined up with the yellow ball, and so are those ones, and so are those ones, and so are those ones, and so are those ones. It doesn't matter how fast you fire it sideways, it's still doing what? Falling at the same rate. If you understand that, you're a long ways away. You're a long ways along. Okay? It doesn't matter how fast it's going sideways, it still falls at the same rate. The path traced by a projectile that accelerates only in the vertical direction while moving at a constant horizontal velocity is called a parabola. When air resistance can be neglected, usually for slow-moving objects, or ones very heavy compared to the force of air resistance, the curved paths are parabolic. If you go to a golf ball, not true because it's moving fast and it's small. Okay, so, question, my friends. Question 1. Oh, gotta do this. At the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released and drops to the ground. So two objects, one being fired out sideways, one is being dropped. Which bullet, the one fired downrange, the one shot way out like that, or the one dropped hits the ground first? Which one hits the ground first? Drop bullet, fired bullet, same time. Could be either one, depends on something else.
What does the second bullet do? I'm confused.
You've got one bullet that goes like this,
Yeah, I got that.
right? And the other one is dropped at exactly the same time.
Oh, you just drop it.
Just drop it. Yeah. Fired, boom, and dropped at the same time. Which one hits the ground first? This is how long it takes a tennis ball to hit the ground. Is that how long it takes a bullet fired straight out to hit the ground? Like, I don't know, 60, 70 meters per second? Which one hits the ground first? Correct answer is C. Well done. The same time. Is that not what this picture shows? Exactly that picture. The only difference is a bullet is fired a whole lot faster at exactly the same time. If only there was a Mythbusters episode where they did this. Same time. If we have time. Okay, so upwardly moving. Consider a cannonball shot at an upward angle. Pretend for a moment there's no gravity. Then, according to the law of inertia, the cannonball will follow the straight line path shown by the dashed line. Why does it go in a straight line path? Objects in motion stay in motion. There's no gravity to pull it down. There is gravity, so this doesn't happen. What really happens is the cannonball continually falls beneath this imaginary line until it finally strikes the ground. Get this. The vertical distance it falls beneath any point on the dash line is the same vertical distance it would fall if it were dropped from rest. Okay, so if I fire this cannonball up like this and there's no gravity, it's going to go in a straight line. If I hoverboard it up to this point right here and let it drop, it would still fall the same distance. The vertical upwards velocity makes no difference on how far it falls. How come? Because gravity is minus 9.8 meters per second squared down, and does it care if you're moving up or down? Or sideways? No. Put it another way. Shoot a projectile skyward at some angle and pretend there's no gravity. After so many seconds t, it should be at a certain point along a straight line path. But because of gravity, it isn't. Where is it? The answer is it's directly below that point. How far? 5t squared, or miraculously 4t squared. Where does that come from? Our friend d equals vit plus a half at squared. And if you just dropped it from there, what would be the initial vertical component? 0. 1/2 at squared. 1/2 of minus 9.8 t squared. What's 1/2 of minus 9.8? 4.9 t squared. Note another thing. The cannonball moves equal horizontal distances in equal time intervals. That's because no acceleration takes place horizontally. I cannot stress this enough, you guys. And yet you're going to do it on the test. You're going to have some sort of acceleration for horizontal. There is no horizontal acceleration. The vertical distance that falls below the imaginary straight line path during equal time intervals continually increases with time. Figure 4 shows vectors representing both horizontal and vertical components of velocity for a projectile following a parabolic path. Notice that the horizontal component is everywhere the same. The horizontal component is always the same. How come? No horizontal acceleration. There is no horizontal acceleration. Have I repeated myself several times? Note also, only the vertical component changes. Here's the vertical right here, right? There's vertical. Why is it differing? Because of gravity. What's the vertical component right here? 0. Note also that the actual velocity is represented by the vector that forms the diagonal directile formed by the vector components. That red one and that blue one will add together by Pythagoras to give you the black one. And that black one gets smaller and smaller, doesn't it? And then it gets bigger and bigger as it goes up and down. At the top of the path, the vertical component vanishes to 0, so the actual velocity there is the horizontal component velocity at all the points. Everywhere else, the magnitude of the velocity is greater, just as the diagonal of a rectangle is greater than either of the sides. This one down here shows the path traced by a projectile with the same launch speed at a steeper angle. Notice that the initial velocity vector has a greater vertical component than when the projection angle is less. This greater component results in a higher path, but the horizontal component is less, so the range is less. If you shoot it high, it doesn't go as far. How come? Less horizontal component. I can see that I'm losing you. Is there two ways for it to hit with the same speed at the same place? Are there two ways to make it hit with the same speed? Two angles. And the answer is yes. Figure 6 shows the path of several projectiles, all having the same initial speed but different projection angles. The figure neglects the effect of air resistance, so the paths are all travelers. Notice that these projectiles reach different altitudes or heights above the ground. They also have different horizontal ranges or distances traveled horizontally. Yeah. The remarkable thing to note from figure 6 is that the same range is obtained from two different projection angles, angles that add up to 90. At 60 and 30, they will land at the same point. One will just go higher than the other. So, which tells me if you want to go the maximum distance, what's the maximum distance? 45. 45 is maximum. In cases where the weight of the projectile, Quinn, you should be listening. In cases where the weight of the projectile is comparable to the applied force as when a heavy javelin is thrown, the applied force does not produce the same speed for different projection angles, and maximum range occurs for angles quite a bit less than 45 degrees. I'm sure that Olympic javelin throwers know what angle to throw it at. It's not 45. If there is air resistance, this is what Steve's path at his golf ball looks like. And it falls like that, right? Why is that? Because in this case there is horizontal acceleration. Is there horizontal acceleration when the Mythbusters fired a bullet sideways? Yeah, they had to account for that. It did actually slow down horizontally. There is horizontal acceleration. Okay, a couple more questions and then the videos. A projectile is shot at an angle into the air. If air resistance is negligible, what is its downward acceleration? I'm looking for a number.
Exactly.
I don't know.
Triangular prism.
Have you seen this?